Okay, so how do we take what we learned yesterday and apply it to what we're doing? So this is in your packet, the tidal wave problem. So let's talk about this. It says a tsunami, commonly called a tidal wave, is a fast-moving ocean wave caused by an underwater earthquake. First, the water goes down from its normal level, then rises an equal distance above its normal level, and then finally returns to its normal level. The period is about 15 minutes. Okay, so we know we got a 15-minute period. I'm going to make a note of that. Period equals 15 minutes. Suppose that a tsunami with an amplitude of 10 meters approaches a pier at Honolulu where the normal depth of the water is 14 meters. Okay, so when they ask us to sketch a graph, they are just looking for a really basic concept here. All right, so if we're reading this, it says up at the top, it says the water first goes down from a normal level, then rises an equal distance above its normal level, and then finally returns to its normal level. So if I just say this is at the normal, let's say we're right here, it's first going to go down from its normal level, so we go down, and then it rises an equal distance above its normal level, so we go the same distance above, and then returns to its normal level. So that, to me, looks like it's a sine function. Okay? Our normal level is 14 meters. So this normal value is at 14. All right? It says we have an amplitude of 10 meters, so it's going to go up 10 from here. So the max that we're going to get is 10 up. That's 24. And then that means we'll also go down 10. So the minimum is at 4. Okay? It says the period is about 15 minutes. So from the start of this wave to the end of this wave is 15 minutes. And they didn't give us a starting point. So I'm going to assume that we are beginning right at the very beginning of this problem at 0. So the tsunami starts at 0, and then 15 minutes later that wave has come through. So we've got all the information that we need to do. Okay, now this is just a really rough sketch, and I'm okay with that rough sketch for this purpose. We just need to get this drawing in so we can figure out what the equation is. So the most important part is getting the equation right. Okay. So let's do this. Let's get this equation right now. So that's step A. Create an equation for this situation. So I'm going to write this down. I'll get our shell. Y equals A plus B sine of C, and then X plus D. Okay? That's the beginning part. So A is our midline. Our middle is at 14. So it's 14. Okay? This graph starts in the middle and goes down. So that's like a reflected sine graph. So instead of putting a plus value here, I'm going to put a minus. So it's a reflected sine graph. So minus sine. B is our amplitude. Well, it tells us our amplitude is 10 meters. We put that in. I'm going to leave C alone to the very end. And then X plus D, well, D is our starting point. Our starting point is right here. It didn't move anywhere. So I'm going to say it's just X or X plus 0. Okay. C is the thing that gives us the most trouble. So our formula yesterday said C equals 2 pi divided by our period. Well, in our case, our period they gave us was 15 minutes. So 2 pi over 15 is going to be our C value. 2 pi, sorry. All right, let's do this. I don't know why it's not working very well. Hold on a second. There we go. 2 pi over 15. So here's our function. All right, don't mind me. Okay, once we have this equation, everything that we do from here on out goes through this equation that we just created. Okay, so part B says, assuming that the depth of the water varies sinusoidally with time, it says predict the water at 12 minutes. So they gave us a value, so we just got to know where to put that value. So 12 minutes, if you think about it, we did 15 minutes as our period. So that's our x value. So they're saying x equals 12. So we substitute that value in. 14 minus 10 sine of 2 pi over 15. And then I get 12 plus 0, or just 12. Okay. Now the best part is this entire thing, they're all numbers on the right side. So we can just substitute this value in. So I go to my calculator. The first thing I want to do is I want to make sure that I'm working in radians. So let's push mode. If you noticed over here, the radians are being highlighted, which is good. Okay, so let's quit out of there. And we can just type this entire thing in. So I got 14 minus 10. Hold on a second. All right, so I do 14 minus 10 sine, and they automatically start parentheses here. So I got to type in this 2 pi over 15 first. So 2 pi over 15. And then after that, I get another set of parentheses. So I'm going to do another set of parentheses and just type in 12. Close that, and then close the argument. All that work, push enter, and my y value is 23.51. So 23.51 feet. All right. C, according to your model, what's the minimum depth of the water? So if I'm looking at the minimum, we already marked it, it's 4. So 4 feet. Okay, so it says, how do you interpret this in terms of what will happen in the real world? And we'll say, as the tidal wave passes, let's see, hold on, I want to make sure I get this right. Oh, it's not feet, it's meters. So as the tidal wave passes, there will still be 4 meters of water. Okay, so let's change this. That wasn't 4 feet, that was 4 meters. I'm going to change this above it too. It's 23.51 meters. You hear my son in the background. Okay. And then D is just a thinking problem that I want you guys to try. So our biggest focus today is taking the information that they give you guys, plotting a really rough sketch of the graph, and turning that sketch of the graph into a function so you guys can use it. Okay? So I did this one for you guys. I want you guys to finish D, and then on the very next page, there's a Tarzan problem. I want you guys to try this Tarzan problem. Work together in a group. You'll struggle a little bit on there, but I bet you guys can do it. And then we'll talk about it when I get back in class the next day. All right, good luck.